Good morning, everyone. My name is Pranay. I'm from CSC AIML Section C. Today, my subject essentials of problem solving. In the subject of essential problem solving, today my topic I'm gonna discuss is living people. So, as per topic of living people, so we have generally graph theory, graph concepts. Using those graph concepts and using the concepts of our graph theory and as well as algebraic equations and other methods, how can we construct in a proper organized manner of living people and living world around us in a proper manner, and how this arrangement helps in how we can plan all the essentials need in living society, living people's world. Let's discuss through our graph concepts and all other concepts. Yeah. Introduction. I would like to introduce about what is a living world and living people. The living world includes all organisms, humans, animals, planets, and microorganisms. Each organism interacts with its environment continuously. These interactions create complex systems requiring advanced modeling. Living world involves movement, communication, growth, and reproduction, adaptation, and intelligent behavior. And next, I want to say understanding these connections help in engineering, city planning, healthcare, environmental management. Living world in engineering context. Engineering analyzes the living world as complex dynamic systems. Human population movement forms real lifetime networks. Living organisms behave like nodes in a system interacting constantly. Applications include smart city development, real-time traffic engineering. So next is emergency response optimization, healthcare and epidemiology, resource distribution modeling. Engineering tools help simplify biological complexity. Why mathematical modeling is needed for this living people or living system. Living systems are too complex to understand directly and helps create simplified models that reveal patterns, helps in predicting population changes, mapping human and animal migration, deciding or designing efficient transportation networks, controlling pandemics, ecosystem preservation. Mathematical modeling converts real world into analyzable data. Next, we'll see that graph theory, introduction to graph theory, and how can we connect our topic to graph theory. The graph means the combination of edges and vertices also called as nodes. So graph theory deals with connections and relationships in our topic. Graph is equal to nodes. Nodes is people or locations. Edges is paths and interactions. So this graph theory is useful for modeling human movement, contact tracing, urban mapping, food web interactions, and there are types of graph that we can also manage in our biological systems. Weighted graph with distances and time, directed graph, one-way direction while people are traveling on a road, undirected two-way directions like we can go through one destination in two-way direction or multi-way direction. So this helps track and manage biological systems in a very dynamic way. Graph construction for living systems. A city is divided into nodes or zones. So the connection between nodes represent road networks, interaction between organisms, and flow of resources. Edge weight represents travel time, distance, and intensity of interaction. Graph structures help identify critical zones, bottlenecks, high density regions, spread of diseases or movement. Graph touring, route optimization. For example, living system require efficient movement like humans or animals. Graph touring will take, for example, the travel salesman problem and will apply in our daily life that we need a shortest path to cover all important locations. For example, the ambulance needs shortest route to reach the patient on time to the hospital. The police patrol needs maximum area coverage to check any corruption or any corrupted people are making place corrupted. The Swiggy Zomato, the delivery boy has to deliver the things or the orders on time, and they require shortest path to cover as fast as possible. And next is public transport planning. Approximation algorithms help to solve these problems, and it will be helpful for the population. And next, graph coloring. We'll use that as we know that in graph coloring theorem, no two adjacent nodes should be having the same color. So here and we know that 4 color theorem minimum optimization color is 4. So now how this graph coloring we can use? So by using this graph coloring, we can prevent overcrowding, we can create scheduled market timings, we can avoid traffic jam, and there will be a proper timetable planning. For example, zone A as red color and zone B as blue color, and so using this way, we can manage in a proper manner. Next, algebraic equation, population density model using algebraic equations. For example, ax square plus bx plus c is equal to p into ax square plus bx plus c, where p is equal to density distribution. It helps in calculate density of people per kilometer square, resource usage, and need of facilities or load of facilities. For example, transport, public, school. Okay, so engineers, they use this equation for smart city plannings. The transcendental equations in population growth. For example, there are many transcendental equations like Mueller's method, Sekant's method, and the Newton-Raphson method, Ramanujan's method. So using all these methods, we can maintain proper exponential and proper logarithmic laws to in order to model the population explosion, spread of diseases, bacterial multiplication, and many other sources. And numerical integration, by using this, we can create the rate of migration, we can calculate movement density, we can calculate animal herd flow, we can calculate football predictions, we can calculate. So we can calculate some real world applications using this numerical integration methods. For example, trapezoidal rule, Simpson rule, RK4 method. This helps model gradual changes over times. ODEs in our living world. Many biological processes are governed by ordinary differential equations. For example, logistic population growth. So the ODE is useful for human population prediction, animal population regulation, epidemic spread modeling, growth of microorganisms, provide realistic future forecasting. Living world system architecture inputs population size, movement patterns, area maps, interaction strength, processing, graph creation, route optimization, zone coloring, ODE simulation. Numerical integration, and outputs will be best routes, safe zones, congestion free models, future population estimate, biological networks, living systems form such as social networks, food webs, neural networks, ecosystem connection graph, and each node influences the other nodes or other places of nodes, so that it will be like completely, it is an interacting system, and we are in the world of interaction. It will be portrayed as in a good way. Next, graph theory also helps in dominance, vulnerability, robust net. It is used in wildlife protection, disease control, resource planning, and many natural resources planning, and the disease control. Like during COVID time, many COVID was spreading. In order to control the COVID, they use some of these principles to do some changes or bring some pandemic to a control. Human movement simulation, like human, they can move, how they are moving during festivals, they can see the migration during festivals from city to town or city to village, for traffic peaks, emergencies like ambulance, natural disasters during cyclone, during tornadoes, during volcano bursts. Numerical models estimate movement density, time-based population flow, zone congestion levels, and help design safer cities and event venues. Application: smart cities predict and control traffic, allocate utilities better, healthcare. Next, for healthcare, the disease outbreak situation, hospital load prediction, transport engineering, bus or metro optimization, road planning, environmental management, wildlife movement mapping, forest resource planning, disaster management, evacuation route planning, safe zone identification. Advantages of mathematical approach: high accuracy compared to guesswork, easy visualization of complex systems, effective in predicting future scenarios, helps avoid overcrowding, supports real-time decision making, cost effective and scalable, integrates multiple fields like biology, engineering, innovations in the approach. First time combining graph theory, travel salesman, route planning, graph coloring, numerical integration, differential equations, transform living world concepts into engineering models, detects patterns invisible to human observation, supports automation and AI based predictions. And I would like to conclude that the living world is complex but mathematically predictable. Graphs efficiently model interactions and movements. Numerical methods help simulate real world behavior. ODs predict population growth and environmental changes. A combination of these techniques provides powerful tools for city planning, healthcare, traffic control, environmental conservation. Engineering mathematics bridges biology with real world problem solving. With this, I would like to conclude my PPT, and I thank each and everyone for giving me this topic, and thank you everyone once again.